Hey everyone, my name is Caroline. Today we're going to be learning about Fick's law of diffusion and physiological applications of said law in body systems and drug diffusion. Before we begin to apply Fick's law of diffusion physiologically, we first have to understand what diffusion is. Diffusion is a transport phenomenon where substances will move from places of high concentration to low concentration. In Fick's law, the rate of diffusion, or termed as variable Q, is determined by the concentration gradient, delta C, the membrane surface area, variable A, the diffusion coefficient, variable D, and the membrane thickness, variable delta X. In the diffusion coefficient equation, there are a few things that go into consideration. One of them being the permeability of the membrane to that specific substance, variable P, and the molecular weight of that substance that is being transported. Diffusion can be enhanced in a few different ways. Membrane surface area, if it's increased, will enhance diffusion as there is a greater availability of space for the substance to transfer across. Diffusion can also be enhanced if there's a stark concentration gradient and if the membrane thickness is reduced, which constitutes a shorter path length for substance transfer. If the substance itself has greater solubility across said membrane and has a lower molecular weight, diffusion will also be enhanced. Alrighty, now that we understand Fick's law of diffusion, let's look at the renal system and how the Fick's law of diffusion applies to glucose reabsorption. Glucose will enter the glomerulus and get filtered in the renal tube. 99% of glucose will get reabsorbed in the proximal convoluted tube as the nephron tries to reclaim glucose. The renal tubule cells are brush border cells with apical surfaces that face the tubular lumen and are lined with microvilli projections that increase surface area. The basolateral surface face the peritubular capillary and run alongside the nephron. In order for glucose to get into the renal tubule cells, energy is required. The concentration of glucose inside the renal tubular cells is often a lot higher than in the tubular lumen. So in order for it to cross, the sodium glucose linked transporter moves it across in secondary active transport, where the glucose transport across the apical surface is driven by the electrochemical gradient of sodium. The sodium glucose linked transporter binds 2 sodium and 1 glucose from tubular fluid and releases them inside of the cell. Here is where Fick's law of diffusion comes in. The intracellular concentration of glucose is so high that glucose quickly moves across the basolateral surface via facilitated diffusion with either the GLUT1 or GLUT2 transporter and makes its way into the peritubular capillary. Applying the Fick's law of diffusion, we can first look at delta C, where there is a high glucose concentration in renal tubule cells compared to the peritubular capillary glucose concentration. GLUT1 or GLUT2 are facilitating glucose transport, which cuts through the issue of having to deal with membrane thickness as well as the molecular weight and solubility of glucose for the basolateral membrane. The surface area increases because there is a presence of multiple GLUT proteins that increase the membrane surface area coefficient until the transport maximum is reached when all GLUT protein transporters are being used. Alrighty, now let's take a look at gas exchange with the respiratory and cardiac systems and how Fick's law of diffusion applies here. So gas exchange occurs in the lungs across alveolar and capillary walls. Molecules impact against these membranes that creates pressure, and the amount of pressure they exert is proportional to the total force of impact of all molecules. However, given that air is a mixture of gases, the rate at which each particular gas diffuses will be entirely dependent on the pressure caused by that gas alone. This is called the partial pressure. Gases move along partial pressure gradient as opposed to the concentration gradient seen earlier. So, when looking at the Fick's diffusion equation here, we're looking at delta P instead of delta C. Delta P is dependent on partial pressure of each gas created alone. So when looking at oxygen, the partial pressure of oxygen is higher in the alveoli compared to the capillary, so it moves from the alveoli into the capillary. When looking at carbon dioxide, the partial pressure of CO2 is higher in the capillary compared to the alveoli, So carbon dioxide moves from the capillary into the alveoli and is later expired. When looking at the diffusion coefficient, the solubility of oxygen in blood is not particularly high, but the oxygen partial pressure is extremely stark, so the partial pressure will outweigh any deficiency in the diffusion coefficient. When looking at the diffusion of carbon dioxide, the solubility of carbon dioxide in blood is actually 22 times higher than oxygen, so it's very high, which outweighs any issues with the partial pressure gradient of carbon dioxide. The alveoli are plentiful in the lungs, so there is an increase in surface area, and alveoli are encased by plenty of venous capillaries, which also increase the chance of surface area maximized for gas exchange. The membrane thickness is also reduced in the alveoli because alveolar walls are only one cell thick and capillary walls are also one cell layer tissues. Alrighty, now that we've made our way applying Fick's law of diffusion to a few physiological systems, let's look at an application of Fick's law in the digestive system with enteral drug administration. So, when a patient consumes a drug, either orally or through an NG tube, it ends up in the gastrointestinal tract. It's absorbed through the intestine, and the portal vein system brings the drug to the liver via capillaries and veins, where it's either metabolized or deactivated and excreted as waste. It's very important to take into consideration Fick's law of diffusion when people are designing drugs because they want to enhance the maximum absorption and efficacy of a drug when it is taken orally or intramuscularly. So, let's look at a patient who is administered 500 milligrams of naproxen orally for a headache. This naproxen travels through the gastrointestinal tract into the stomach, and there is minimal absorption that occurs in the stomach for drugs, so the drug continues into the small intestine. Naproxen will actually be absorbed majority in the proximal duodenum because it is a high acidity environment, and we'll figure out why that's so important later when applying the equation of Fick's law of diffusion. So to begin, when looking at the rate of diffusion of naproxen, we'll start by beginning at delta C, the concentration gradient. Given that there was no naproxen circulating in the blood of this patient prior, the concentration gradient is pretty stark as there is a high concentration of naproxen in the proximal duodenum fluid compared to the blood. When looking at the surface area, variable A, the duodenum has microvilli that increase surface area by allowing for maximum transfer of the drug across the lumen. Okay, so the diffusion coefficient is where this high acidity environment of the proximal duodenum comes into play. So naproxen is a small molecule, meaning it doesn't need a transporter to transport across the membrane. It is also hydrophobic, so it travels easily through the lipid bilayer and is nonpolar. It is given in its weak acid form, so it is highly soluble in an acidic environment. All of these characteristics of naproxen all help increase the absorption of the drug. The delta X, or membrane thickness coefficient, is also relatively low because the capillary membranes are one tissue layer thick, which allows for a capillary bed to have a relatively low membrane thickness and easy diffusion of a drug from the intestine into the capillaries. So, just to quickly recap, there is passive diffusion of the naproxen drug across the basolateral membrane of the duodenum into the capillary bed because of the high concentration of the naproxen present in the proximal duodenum compared to that in the capillary. Naproxen has a small diffusion coefficient as well because it does not need a transporter, it is hydrophobic and nonpolar, and it is in its weak acid form. There is a very high surface area of all of the microvilli that are present in the duodenum, and the capillary membranes are one tissue layer thick for a reduced membrane thickness. Here are my references. Thank you for watching. I hope this helped.